In this video, we provide the full pseudocode of the quicksort algorithm. So as you remember, the algorithm is recursive. For this reason, we pass to this procedure, to the quicksort procedure, the array A, and also two indices L and R in this array for left and right. And this procedure sorts the subarray inside R with indices from L to R. Well, we first check whether L is at least R. And if yes, then this means that the corresponding subarray contains at most one element, and this in turn means that nothing needs to be done, so we just return. Otherwise, we call the partition procedure with the same parameters. It returns an index M between L and R. So it rearranges all the elements inside this subarray with the following property. After the call to this procedure, A of M stays in its final position, meaning that all the elements to the left of an element A of M are at most A of M. And all the elements to the right are greater than A of M. Well, once again, after the call to the partition procedure, A of M stays in its final position. So what remains to be done is to sort all the elements that are at most A to the M, they stay to the left of A of M, and all the elements that stay to the right. So we do this just by making two recursive calls. So this is how the whole algorithm looks pictorially. Again, we are given an array A with two indices L and R, and we are going to sort a subarray inside R with indices from L to R. So we first call the partition procedure with parameters A, L, and R, and it gives us an index M between L and R with the following property. All the elements to the left of M are at most the element A of M. All the elements to the right are greater than A of M. Then we make two recursive calls to sort the left part with indices from L to M minus 1, and to sort the right part with indices from M plus 1 to R. And immediately after these two recursive calls, we have a sorted array. So before showing the actual pseudocode of the partition procedure, we explain its main ideas again on a toy example. So first of all, we will take the element A of L and denote it by X. This will be called our pivot element. So a pivot is exactly the element with respect to which we are going to partition our subarray. So X will be placed in its final position. So our goal now is to rearrange all the elements inside our current subarray so that X stay in its final position, and all the elements to the left of X are at most X, and all the elements to the right of X are greater than X. So we will do this gradually increasing the region of already discovered elements. So for this we will use a counter I, and we will maintain the following invariant. So I will go from L plus 1 to R, and at each point of time, when we already read I elements, we will keep two regions inside this region from L plus 1 to I. In the first region from L plus Y to J, we will keep all elements that are at most X. In the second adjacent region with indices from J plus 1 to I, we will have all elements that are greater than X. Okay, let's see at our example. So I assume that we are somewhere in the middle of this process. In this case, X is equal to 6, and we need to partition all the elements with respect to X. We already have two subregions. So in the red region, we keep all elements that are at most X, that are at most 6. In the blue region, we have all the elements that are greater than 6. Okay, now we move I to the next position, and we discover the element 9. So this element is greater than 6, so we just need to extend the second region, the blue region, the region of elements that are greater than 6, right? So in this case, we just do nothing. Well, the next case is more interesting. We move I to the next position, and we discover the element 4, and in this case we need to somehow move this element to the red region, to the region of elements which are at most 6, right? So to do this, we just swap it to with the currently first element of the blue region, in this case with 9, right? So if we do this, 4 will be the last element of currently red region, and 9 will go to the blue region. So we do this, and now we increase also the value of G just to reflect the fact that our red region has just been extended, right? Then we move I to the next element, so we discover element 7, which is greater than 6, which means that we can just extend the blue region. Then we discover another element, which is 6. 6 is at most 6, and this is actually equal to 6, so we need to move it to the red region. Again, we swap it with the first element of the blue region, and then we extend the red region. I mean, we increase G to reflect the fact that the red region has just been extended. Then we discover another element, which is at most 6. We move it to the end of the red region. And finally, what we also need to do in the very end is to move the pivot element, which is 6 in this case, to its final position. And its final position actually can be easily found in this case. So we have red region and we have blue region. In red region, all the elements are at most 6, and in blue region, all the elements are greater than 6. So we can just swap 6 with the last element of the red region, right? In this case, it is 1. So if we swap these two elements, then you can see that all the elements in the blue region are indeed greater than 6. All the elements in the red region are smaller than 6. So we are done with this partition procedure. We are now ready to present the pseudocode of the partition procedure. Recall that what we're going to do is to place some element x, which is called the pivot, into its final place, so that all the elements before x are at most x, and all the elements after x is greater than x. So as the pivot element in this procedure, we are going to use just the first element of the corresponding subarray. So x is assigned A of L. We are also going to maintain the following two subregions. So first of all, we will gradually increase the region of discovered elements. So I goes from L+1 to R, and inside this region of already discovered elements, we will maintain two subregions. In the first region, with indices from L+1 to J, we will keep all the elements that are at most x. In the second region, with indices from J+1 to I, we will keep all the elements that are greater than x. And we will gradually increase the value of I. So when I is increased, so assume that I has just been increased. So we discovered a new element A of I. So if A of I is greater than x, then just the second region of elements that are greater than x is extended automatically, and we do not need to do anything in this case. However, if the newly discovered element is at most x, then we need to move it to the first region, right? So we do this as follows. So we just increase the value of j to indicate the fact that, well, the first region has just been increased, and then swap the elements aj and ai, okay? So this way we just maintain our invariant each time when I is increased. So in the very end, when I reaches the value of R, we also need to place our initial element that stays at the beginning, our pivot, between our two regions. So for this we just swap elements A of L, so this is our pivot, with element A of J. And we then return the value j as an index of our pivot element.